I'm really pleased to welcome Ari Chaudhra to speak today. She is a systems engineer at the Canadian Space Agency. She has a PhD in laser physics from the Max Planck Institute in Hamburg, Germany, where she specialized in high-energy lasers and worked as a scientist at the European X-ray free electron laser facility. And her talk today is Applications and Design Guidelines for High-Power Lasers in Space Exploration. So I'll turn it over to you.
Good morning, everyone. I'll just move this down. Is this better? Yeah, awesome. So thank you so much for being here, and I'm really excited to talk about this. So why high power lasers? So we had these wonderful presentations. There's going to be some more about visionaries and cosmologists and astrophysicists talking about all these applications. And the engineer in me starts wanting to roll up my sleeves and say, okay, so how can we make this happen? What's stopping us apart from the funding? So this presentation is an overview of the nuts and bolts of high-power lasers, because I find that innovation happens at the intersection of two really well-developed fields. So there's a lot of work going on in extreme light, and there's a lot of work going on in space exploration, and where do these two intersect, and how can we take advantage of the maturity of high-power lasers? What do I mean by high-power lasers? So there's 2.5 worlds here that I want to talk about. The first is high average power lasers. So these are continuous or pulsed powers. That's the half, which is continuous wave, where you get extremely high output, average output over an extended period of time. So the relevant equation here is average power is E, the energy, times the repetition rate of the laser. And we have high peak power, where there's a high amount of power in an ultra-short duration. So on the left side, you're talking about nanoseconds and up pulses or continuous wave. On the right side, we're talking about attosecond and up wave pulses. And the peak power is defined by the energy in the pulse divided by the temporal duration of the pulse. So just looking at the electric field, on the top you have a CW wave electric field. You know, it's oscillating, it's there. On the bottom you have pulse. And when you zoom in on any one of those pulses, you see that they're built up of a large number of frequency components that are interfered to create this one very short peak power pulse. So yesterday we had that presentation about Raman and why wavelength actually matters. And it matters because of the potential energy surface. So on this graph, this is the potential energy surface, and this is the internuclear distance between the two vibrating atoms in a diatomic molecule. Really simple. But each one of those lines on the bottom is a vibrational energy level. Okay, so the molecule is vibrating, and this is the ground state. When you photoexcite this jumps up to a completely different electronic state, But on the bottom, you have these vibrations. And in between each one of those lines on the bottom, you have the rotational levels. So that the smaller the distance, the lower the energy, the longer the wavelength. So your rotational and your vibrational modes are in the infrared. So the stretch of single bond stretches happens at around 3,500 wave numbers, all the way down to the mid-infrared, which is called the fingerprint region, because each molecule vibrates in a certain very specific way, and that bond inside a molecule will behave in a very specific way. And this is the fingerprint region, and this is why the mid-infrared and Raman spectroscopy happens in this region. And why pulse width matters? It matters because of intermolecular vibrational redistribution. All of these vibrational modes of this molecule are coupled. So it's like a pendulum oscillating in an n-dimensional space. As soon as you pump, let's say, or energize the stretch with a picosecond pulse, so 1,000 femtoseconds, after that time, the energy starts getting redistributed through coupled ways into different modes. So the molecule starts bending instead of stretching. And then it starts rotating. And then it starts librating. And by the time you get to the libration level, this is for water. Water is very, very tricky to deal with, because as soon as you pump the stretch, very shortly after that, 30 femtoseconds, you are now librating. And now you just built a really, really expensive Bunsen burner. So the pulse width matters depending on what you want to study or what you want to energize. So we deal with that in the fundamental science community with extreme high peak power lasers. So this is CLF. And these lasers span, entire buildings here. But there's a lot of work happening in miniaturization and efficient use of space because when I started at the XFEL, which is the X-ray free electron laser, it's a LINAC injector laser. I was responsible for the injector laser. It spanned from one end of this room to the other, all the different stages and the amplifiers. And within a couple of years, my laser was, the size of this table over here. So a lot of this is, of course, support and vacuum support equipment, which we don't need in space. And these are some of the highest extreme light power lasers that are out there. I mean, there's the National Injection Facility, of course, 90 petawatts, 20 nanosecond pulses. And then, there's Vulcan at the Lawrence Livermore. And all of these are petawatt and terawatt peak power pulses. Obviously, the duty cycle is super low. I mean, these are not firing continuously. The best you get is 10 hertz out of it. Usually for a little less power than this, the injector lasers at LINACs will work in the kilohertz range, megahertz range. And notice that, look at the gain medium. It's neodymium, TiSA, 1 ytterbium, and I'll talk about in a couple of slides as to why it's these gain materials over and over again. And this is not a true equivalency, just for fun, let's talk about these lasers in numbers of Hiroshimas. So the NIF facility is 2.4 million Hiroshimas in terms of peak power. Okay, and down to a few thousand times Hiroshimas. So high average power lasers, these are much more interesting for metals processing, military applications. That's the IPG Photonics Wireless 100K, and I'll give you the specs for it in a moment. On the right side, we have Athena from Lockheed Martin, and these are compact. These are well developed in terms of power, in terms of everything else. I mean, those look ready to launch. Slap a few solar panels on it, we're ready to go. These guys are all ytterbium. Take a look. These are ytterbium, some gallium arsenide, and the average power is in the kilowatts range. But remember that lasers can be combined once they're coherent radiation, so you can do a lot with only 100 kilowatts of power. And for metals processing, materials processing, the spot size, so when you focus it down, it's about 100 microns to about a millimeter. And when you have that kind of average power and peak power focused at that intensity, you get megawatts of intensity, so per square centimeter. Okay, so again, and a false equivalence, but let's assume the radiant solar intensity at the surface of the sun. How intense are these lasers? They're about 100 to 2,000 times the surface intensity of the sun. So cool lasers. And you can buy one for a couple of $1,000,000. Just send them an order. They're waiting off the shelf. So let's talk about laser parameters and what drives these laser systems. Repetition rate, obviously, as I said, this is the duty cycle. This is where the thermal load comes in. And the peak width, the pulse width, that's dependent on the gain dynamics, nonlinear effects, plasma, and damage. Really, the peak width, the pulse width, and the peak powers are limited by the damage in the medium. Population inversion, this is the core principle of lasers. Essentially, you have atoms, and remember that diagram that I showed you about the potential energy surface. They're all sitting in the ground state, vibrating away. We pump them with something. Back in the day, there were flash lamps. You can do optical pumps, electrical pumps. And when they're in the excited state, you find a way to extract the energy. So this is the sort of the temporal dynamics of it. So you pump it with this long pulse, and your atoms or your molecules start going into the excited state. This is the number of molecules. But there's a limit. There's a threshold to this. And this is dictated by IVR, gain dynamics, quantum efficiency, a whole bunch of factors, thermal losses. And so what you want to do is time it right at that peak before it starts to decay and lose all of that energy into waste heat. You send a pulse or something else that will stimulate the emission and extract the energy efficiently from this. So this is where I want to talk about why we use these gain media. So neodymium is used because it has an extremely long energy storage lifetime. So you can pump it for microseconds. So that means that it can gather a lot of energy, and then when you send your emission pulse through, you can extract a lot of energy from this. Titanium sapphire, it's a high emission cross-section and really, really good thermal properties, which means you can extract the energy and it doesn't heat up. There's another reason, nonlinear. We'll talk about it in a minute if I have time, or ask me about it later. Maybe we don't have time. And ytterbium, why you see ytterbium in all of these other systems is that as a fiber, it has exceptionally good thermal qualities. So that means you can pump it. It has a really good emissions cross section. You can energize it, and then in a fiber, instead of having the fiber break down, it conducts thermally, and you're good to go. Very low losses. But all of these parameters for extreme high power lasers are very interlinked, and we don't think about them for normal power lasers. But essentially, if you increase population inversion, increase the energy extraction, that increases your laser power, great. But that decreases the beam quality because when the power goes up, any instability is magnified. And it increases the thermal load, which increases the spectral instability, which increases the phase noise, which decreases the coherence of the laser, which increases the pulse width. As soon as the pulse width is wider, your peak powers have dropped by orders of magnitude. So now, ideally, if the peak power drops, then your thermal load should drop, but it doesn't always come back. So a good laser engineer, a good designer, physicist will work on creating a steady state because you want stable output, right? You don't want one pulse coming out at megawatts, another pulse coming out at gigawatts. I mean, it's not good. So you want to create a steady state system and remove the heat as efficiently and as well as you can. And in space, this is not a straightforward proposition. So let's talk about nonlinear effects. This was my bread and butter for a little while. In extreme high power lasers, you get to a point where the electric field of the light becomes so strong that it induces nonlinear responses in the medium it's passing through. So it's the intensity-dependent refractive index changes. And this is called the Chi-3 susceptibility. And sometimes it's good, like third harmonic generation, you can use these nonlinearities to create new frequencies of light. You can mix for different frequencies of light, which requires some phase matching. But the light also self-focuses it. Just its own intensity acts as a self-focusing mechanism inside bulk media or inside any other nonlinear media. You get two-photon absorption, multi-photon absorption, where you can use infrared light to do photo transitions in the UV. Why? Because you are absorbing multiple photons simultaneously because the intensity is so high. So self-phase modulation, self-focusing, two-photon absorption, all of these can be utilized for high-power lasers to do all sorts of very interesting things. But at the same time, these create damage. These limit the power that you can get. Once you get a certain intensity, you start producing plasma. The plasma is great because you produce self-filamentation. You lose energy for inverse Bremsstrahlung, but after you will damage and degrade your material very, very quickly. So, I mean, this is what happens with the pulse. In the temporal domain, you start with a high power pulse, and suddenly you've got pulse splitting. You get walk-offs. In the spatial domain, I mean, you're getting this self-steepening and this self-focusing effect, but you're losing energy, you're losing quality. And imagine extreme high powers, gigawatts, megawatts of power being focused on an optic, and the pulse looks like this. It's very difficult to maintain. All of these systems are multi-stage systems. So this is my laser at XFEL. I start off with IR light, 1064, 1032. Frequency double it twice, get it UV, send it down 2 stories to the injector, where you create electrons, and the electrons head on their way to make X-rays at the end of the 1 kilometer long tunnel. There's a laser heater here to heat up and redistribute the energy in the electron bunch. So space challenges we can overcome. Thermal. Assume a maximum conversion efficiency of 20 to 30%, and that's right when the system is brand new and shiny and everything works perfectly. The rest is waste heat. So the NIF, ELI, which is the extreme light infrastructure in the Czech Republic, they use 10 to 13, sometimes 20 megawatts of electrical power from the grid, and majority of it is used for cooling systems and vacuum maintenance. For a typical extreme high power laser, assume a kilowatt of waste heat from the lasing process, this waste heat from the laser, not any other electronics or anything else. And so about 100 kilowatt for some of the large laser facilities. My laser was running at about 100 kilowatts of waste heat. The ISS heat removal capacity was about 70 kilowatts, more or less. It depends on the time. So this is doable. I mean, ISS is old tech, right? We can do better than this. So it's in the realm of possible. The mass properties are more interesting because try telling a laser designer that they need to consider the inertial properties of their mass inertia of their laser beamline, and they can't have their beamline the way they want it because, it's unbalanced. You can't launch it. Stability versus mass. The way we do stability is we make the the mounts as heavy as possible with multiple points. It's not good for launch. You start removing mass, you lose stability. The material laser interactions. A lot of the lightweight materials we cannot use in the laser labs because the light, especially the high intensity light, interacts in very strange ways with some of these things, and you'll get material degradation of outgassing that you did not expect. Vibration thermal cycling will destroy any seals after some time, and the laser-induced thermal effects will also cause some problems. Radiation. What it'll do specifically to the optics is you'll get darkening and damage to the refractive index because you're creating color centers, UV degradation causing discoloration, loss of transmittance, degradation of coatings, introduction of color centers, damage in refractive index, and you'll also get lattice defects inside here because of radiation. And when you have lattice defects, this is exactly where cracks start. This is where material breaks start. So you have a megawatt laser focused on this point, radiation knocks loose some pieces of the lattice, you start microscopically propagating your cracks, and at some point, you have a catastrophic loss. You either have like a massive loss, or I've seen optics explode. So because of material defects. And they may have been perfect when they were launched, but they're not perfect after 10 years. Surface contamination. This is a huge deal. Surface bulk, thermal effects, and long-chain carbon molecule buildup. Anytime you have UV high-intensity lasers on the surface, you'll have long-chain carbon molecules building up that need to be cleaned off after a while, or they will create exactly these kinds of defects. Localized heating is a huge problem for NIF and for many other extreme laser facilities. Laser safety and maintenance. It's a super complex working environment for aligning and maintaining these systems. Anywhere from the order of once a month to once a year, somebody needs to go in there, realign the laser just because of drift, just because of things that are not working perfectly, vibrations, all sorts of thermal effects. So somebody needs to do this. Either it's a robot for high energy lasers, you need to do it because otherwise you lose orders of magnitude of power. So either a human needs to do it, robotic systems need to do it, but somebody needs to do it. Clean room standards, as everybody knows, the ISS has a very funky stink to it. Humans are not the cleanest creatures, and maintaining clean room standards in a small space environment. You need to wear a lot of laser protective equipment. The goggles are the most important part, and color perception challenges can show up. Your cameras, by the way, if you've got robotic cameras looking at your laser systems, after a while, your sensors will degrade because you're looking at a laser. Silicon-based sensors, they will degrade. So product and quality assurance. What do you do when you want to fly a laser, even if it's a cheap laser? You don't buy one laser. You buy 40 of them. And based on the yield curve of the laser, how many of them fail? You're playing the silicon lottery at the end of the day. How many of these lasers fail? You got to run them 2 to 5 years before integration with your spacecraft. Run 40 of these arrays continuously and then select the 2 that survive the process the best. Now, when they're $1 million lasers from IPG, you need to buy 40 of them to fly one. Okay. But, I mean, that's just a money problem, right? We've got people to deal with that. So what is the mitigation for high-power lasers? And there's no magic answer here. Unfortunately, it's sealed, shielded spares. To begin with, sealed because you need a hermetic seal on it to ensure degradation that's happening to your operational laser is not happening to your spares, and they need to be heavily shielded. Rad hardening, fault tolerance, all of the standard space stuff. But you need a realignment maintenance budget. So a significant portion of your mass and power budget is going to have to go to monitoring and aligning these systems, maybe robotic maintenance, and size. And in space we want to make things smaller, but in this case, size is a fantastic mitigation. So my BBO crystal, when you shoot at it enough times, there is material degradation. You get spot damage. All we do is we make the crystal bigger, and we have a good, reliable stage, and it just moves the crystal over a little bit. And after the end of 2, 3, 4 years of operation, you've got these little drilled holes into it, but you just move to a new spot in the crystal. So size is a great mitigation for a lot of these things. Applications. So we focused a lot. I mean, there's a lot of wonderful presentations coming up, so I don't want to take away anyone's thunder. But so I want to focus on the human a little bit. There's a lot of challenges for medicine in space. There's a lack of specialists, surgeons, dentists. How many scalpels and dental drills can you fly? There's biohazard contamination control, unknown pathogens, and there's unique space-based issues. So there's increased rate of cancers and rare cancers. Bone and tissue degradation, there's a time crunch. We assume that every astronaut that's flying is important and they can't take a lot of time for recovery. And the normal healing stimulus, the gravity, pressures, things like that, may be missing. So I want to show you what the advances. So here you on the extreme right side, we have the scalpel, which creates a huge damage zone and it creates shear stress. Normal lasers, these low-power conventional lasers, you burn the tissue. But now you look at the pearl laser, which is well-developed. 3 microns, it hits that water absorption bond perfectly in 2 picoseconds. And it vaporizes, just dissociates the bond. And there's no burn, and the tissue that's coming out of it is intact, so you can just analyze the plume for cancer cells instead of taking biopsies while you're doing the cancer. So this is how they do cancer surgery, right? You cut in, and then you take a little biopsy, you check if there's more cancer, you dig a little bit more, you dig a little bit more. Here, you just analyze the plume coming off because the cells are intact. You're not burning them. Laser laryngeal surgery is an example. Apart from neurosurgery, this is one of the most delicate surgeries in the world because any scarring left on the larynges in the voice box the person will lose their voice. So you use fiber lasers attached to the endoscope, and you can do this extremely delicate surgery robotically and virtually. LINAC radiosurgery, they take beams of gamma radiation and they focus it in such a way that it only comes to a focus at the position of the tumor and just penetrates into your head and destroys the tumors right then and there. Laser dentistry is extremely developed right now. You don't actually need to drill into your teeth anymore. Just use a laser. And these are mature applications because they're being used in humans every day. And these can be most easily transitioned to space. Issue in materials processing, we talked about this, metal forming, mining, laser additive manufacturing, in-situ construction. Here's the lasers, you can use them, you can buy them right off the shelf. Laser propulsion, I won't go into this in a lot of detail because I know there's other presentations coming up. But the challenge is this footprint and the size. The powers exist to fuel what you need to fuel. But it's a facility that's, a 3-story building. So we need to do something about that. But the physics problems have been solved. Now we just need funding. Laser comms. So ground to space links already exist, so I don't need to talk about them. In-space communication networks already exist. Interstellar communications. I was looking at what powers and wavelengths we need. So there was one that has specific wavelengths. This is the 1.3 micron band, nanosecond pulse, 5 joules pulse energy, 5 gigawatt peak power. No problem. This is doable. This is some of the accelerators that are running there. So instead of going into a beam dump or that 10 meters of concrete that's stopping your beam from killing somebody on the other end, just point it up. The safety guys will not like this at all, but it's doable. Remote sensing and survey. This is where the high power really makes a difference because spectroscopy, we in libs, we think of as low power from my perspective. Okay, and some people think it's high, but from my perspective, it's low power. But a question was raised yesterday. What are you sure you want to hit the mid-infrared? Maybe you need some different wavelength. Well, we utilize these nonlinear processes with extreme high power lasers and go anywhere from the deep UV to the far infrared with a single laser, 3 microns with a supercontinuum generation and with an OPCPA there, something as big as this table can produce any wavelength you want at extreme high powers. It's hazard detection. It's not a good idea for either your rover or your person to be, 7 meters, which is our distance right now, 7 to 10 meters away from a hazard. You may want to be way further than that. So the extreme power gives you that. Higher SNR, obviously, and a bigger sample spot. You don't want to sit there, sampling the face with tiny 10 micron holes all over the place. You want a big sample, collect the plume, analyze it, and high powers do that. Field anomaly detection. There's a huge problem with navigation, inertial navigation. I'll move really quickly. LIGO, atomic interferometry, laser management of impactors, power transmission, tractor beams. Fantastic. So, references, if you want them, lots of good reading.
That was one of the fastest, most thorough wrap-ups I've ever seen. So you did great. We have time for a few questions. I wanted to make sure we had time for that. Any questions from the audience?
I just have a very basic question. What is the electrical efficiency of these high-power lasers?
That's a fantastic question. And for the commercial For the commercial applications, like 10%. For the other applications, we don't calculate it because it doesn't look good.
Might be under everybody's. But are all these synthetic now? All these crystals?
Oh, you mean like lab grown? They have to be. Yes.
That's
Yeah,
right.
yeah,
I
yeah.
just assumed that, but I wanted to ask if you even worry about the
Purity?
the purity.
Yes, because once you start growing them, you start creating new things like calcium fluoride, which was a mystery for quite some time as to why in the UV it suddenly starts showing this depolarization behavior. And it turns out the way it grows using the Chokolsky method, it starts preferring a certain axis. So halfway through the growth, it starts leaning over to one side and it shifts. So the synthetic process also creates some issues. But yeah, they have to be for the purity.
We're going to take our coffee break, and that's to run from from now until about 10:45. We want to start our next paper at 10:45. Thank you very much.